Greetings in 2026 to maths phonetics, physical science phonetics, as well as grade 12 students. Whether it's a student who is going to be upgrading this year or a student who is new to matric in 2026. Now, I do hope guys have had good holidays and you've made a transition to 2026 nicely, with no serious events, or at least no bad experiences. Now folks, tomorrow you're gonna hear about your results, and essentially some of you may not be very pleased. Anyway, we have done a review of the maths papers, both paper 1 and paper 2. Yes, there are some areas I do feel need a bit of fixing, because I kind of realized as the videos have already been published that there is some issues, and of course one of them in paper 2 was highlighted by one of my supporters. So I'm gonna fix those on the descriptions of those videos. Be on the lookout. Now we're going to handle physics paper 1. Right, so this was the November paper, and we're just going to walk through this question for question. Today we're going to essentially handle MCQs, which is question 1. Right, now let's have a look at the general instructions. Which ones tend to affect MCQs as well? It's usually the issue of rounding off, especially where we have numerical answers. Otherwise, perhaps this portion of the the second instruction, that we need to answer all the questions in the MCQs. Otherwise, usually it's the local instruction that takes precedence here. Now we're told here that various options are provided as possible answers to the following questions. Each question has only one correct answer. We are then to choose the answer and write only the letter A to D next to the question numbers 1.1 to 1.10. And here's an example that for question 1.11, the correct option is E. Now this is to suggest that there's only one answer expected from a student. Now there is a scenario, or there may be a situation where there may be more than one correct answer for a question. Again, this is to test whether the student can adhere to instruction. If there is 3 equally correct answers for the question, then just write one answer. Do not write all, okay? That's just the idea here. But usually when there is more than one correct answer, there's usually one best answer, and that is the answer to look for. To the other seemingly correct answers, there's usually a catch in them. So be on the lookout for that. So as we walk through these questions, I'm going to demonstrate to you guys how to ensure that you are answering the question instead of being misled by a kind of fleshy answer as an option. Right, I don't know what this is doing. It's irritating me actually. Right, now 1.1 says the resultant force, I hate this word, I wish someone can stop using it. The resultant force acting on an object on a horizontal surface. Now, we need to think about a smooth versus a rough surface, right? These are the things we need to consider. So don't just read questions and run into the options. Ensure you understand the opening statement. Now, this is always, can you see guys, it's not a situational kind of a situation, if I was to speak that way. But this is something that defeats all odds, essentially. Right, when we talk of a resultant force, we already know we're talking about Newton's second law, right? because that's the law in physics, or the principle in physics, which introduces this so-called resultant force. Anyway, let's have a look. Option A says this resultant force is in the direction of motion of the object. Now the question is it always the case? Now, you may know, folks, that there may be a situation where an object placed on a smooth, usually when you see a smooth line without any raggedy structures, or should we say any description that there is friction. Now we're going to assume this is the situation where there is no friction. Now we've got an object with an applied force to the right, and essentially our object is moving to the right. Now we can see that this force here becomes the resultant force, because it is the force causing motion in this object. Now this resultant force is certainly in the direction of motion of the object. So this is somewhat correct. But is it always the case? That's where the trick is. This is somewhat correct. It is possible. Now, how about the very same object enters a rough horizontal surface? Right. And we remove our our applied force, so that the only force slowing down this object is the frictional force. Now this would be Fk, because this is a moving object, so we talk of a kinetic friction. But the object would still be moving in the forward direction, but slowing down. Right? But now here's what we realize. We realize that our frictional force is in the opposite direction to that of motion, and it is essentially the resultant force in this case. So we can see that, well, since the surface was not clarified as to which type it is and exactly what was happening in this scenario, we can say that this is both a yes and a no. So this is a partially correct statement, but it's not a situation that we can safely say is always the case. Now, the resultant force is in the direction of acceleration of the object. We know this is true at all times from the law itself, Newton's second law. Right? Because by definition, we are told that when a non-zero resultant force acts on an object, it causes that object to accelerate in the direction of the resultant force. Now, this is at all times. Now, is it zero when the object moves at constant acceleration? Now, remember, we know that from Newton's second law, there's two proportionalities that we need to think about. We know that the resultant force is directly proportional to the acceleration. Now, this suggests that if the acceleration is constant, and so the resultant force will be constant, but it is non-zero, because for us to achieve an acceleration, it must be non-zero. So this statement is incorrect. It is increasing. Again, is that the case? When the object moves at constant acceleration, as we said, the acceleration is directly proportional to the resultant force, such that if the acceleration is constant, and the resultant force will also be constant. So this is incorrect. Now we know for sure that we are not being misled by option B. We have weighed each option and made the right choice. So this is very important, because A and B can be quite difficult for students to separate which one is the correct answer. Although C and D, if one understands the law in question, it's easy to tell them apart. Right, 1.2 reads, a hot air balloon is moving upwards. So direction in physics, guys, is very important. And it is doing so at constant velocity. Now, this is a big statement. It means two things. it means the resultant force, F res, is equal to 0. And this also applies the fact that acceleration is 0. So this object is not accelerating because the velocity is not changing. This is very important to remember when we hear that word, constant velocity. Now, a small stone is dropped. Now, what is the significance of that word? It means the initial velocity of that stone, since it is being dropped from a moving object, it will be the same as that velocity of the moving object it is dropped from. But as soon as they separate, different laws of physics are going to kick in. So their motion may not be the same after that. Right. So we know that this stone is dropped from the balloon. Now, the question is, which one of the following graphs represents the motions of the balloon and the stone? And if we ignore the effects of friction for the stone, what are we creating here? We are making the stone the so-called a projectile. Right? And we are essentially doing VPM. And we know that in VPM, the resultant force, the FRS, is the gravitational force, Fg. And it is always directed downward. And if this is the case, we know that this causes acceleration G, which is also downward. So this means for the stone, this stone is going to accelerate due to gravity, because this is now the only force acting on the stone. So can you see, guys, from the statement and the given information, we can identify exactly which topic is involved here. Now, option A says, this is velocity versus time graph. So on a velocity versus time graph, we already know that, okay, we understood that the initial velocity of the stone and the balloon should be the same because the stone was dropped. So this is correct. So this graph from where it started is very good. But seeing that the velocity of the balloon, since the balloon is moving upward, we know that the balloon was moving upward. Now we can see that this velocity is positive because it's above 0. So this means for this graph, upward was taken as positive. Now this is very important, guys, because remember, given information has a catch in it. Now we can see, okay, the balloon was moving upward at constant velocity. We can see this gradient is 0. So if we look at the slope, the gradient is 0. So this is good. It's not changing. But now for the stone, we know that this is a projectile. So its trajectory, it will be such that it decelerates. Now, a deceleration due to gravity is not going to be a positive slope. It should be a negative slope. Right? Because what did we say? The gravitational acceleration is downward. It's not upward. So this is a positive slope, in which case it means this is not representative of a downward, because we can see that the examiner here chose upward to be positive. Hence, the slope for the stone, because it will definitely accelerate due to gravity, or we can even say it decelerates due to gravity, but I guess it's safe to just say it accelerates due to gravity, because there is a time when it will decelerate to the maximum height, but from there it starts accelerating down. So that's why I'm just not going to use the word deceleration, but keep to acceleration due to gravity. So the slope is wrong, guys, because this means downward, because this slope should represent a downward trajectory. So it cannot be positively deflected, or should we say it should not be a positive deflection. So as a result, that option is out. Let's look at B. B is suggesting a similar scenario as A, in that the starting velocity is upward and essentially it is positive. So we can see that up is also taken as positive here. And we can see that the gradient for the balloon, since it is directed upward, is good. So this is good. But now what happens to the stone? It decelerates, and we can see this is a constant deceleration because the gravitational force is constant here. So we can see that this is a constant deceleration, but in the negative. So this is good because this is negative. The gradient is negative, and it is suggesting a downward trajectory, which talks sense in terms of what we have. So we can see that, okay, this one is good because we also know something, that at maximum height, the velocity decelerated from that of the balloon to 0 before it started accelerating downwards until it hits the ground, if it does. So this portion here also is capturing that fact. So option B ticks all the boxes, but remember, there's usually a catch. So whenever you've got a graph, you have to sit down and think about it. So don't answer questions on graphs when they are complex in nature carelessly. Now, option C says the initial velocity of the balloon and the initial velocity of the stone are different. So this is already wrong. So we are not going to worry about the rest. It's already wrong from the beginning. Option D is saying the same, that the initial velocity of the balloon and the initial velocity of the stone is different, and this is nonsense. But there could be a catch to students who think that a stone dropped without mentioning dropped from what is always going to have an initial velocity. Sometimes when we say dropped, we suggest a 0 velocity. But if it is dropped from a stationary object or a stationary position, so this could be misleading for some students. But again, it's not that bad. So we can already see that the correct option is B. And guys, you can see this takes a moment to go through. So, but of course, a well-trained student would know that option B was the correct answer. But don't be complacent. I have learned in physics that even when you know the correct answer from the outset, you want to weigh the other options because there might just be a small defect in what you thought is the best answer. And only to find that what seems odd is actually the best answer. It helps to ensure that you don't get misled and you do not get to make a careless choice here. Right, 1.3 reads, a motor fixed to the ground is used to lift a box vertically upwards at a constant velocity. Can you see that word? We already know two things. Resultant force acting on the box is 0. 2, we understand that there is no acceleration from Newton's second law. Right. Now we can see that the tension on the string here will be directing a force upward. This we can say this is the applied force, or we can simply call it the tension. And technically this is the force by the motor indirectly. And essentially there will be another force acting on this block or box downward, which is the gravitational force, Fg. And on top of this, we know that there would also be a force that is extra, because as this moves through the air, there will be a force due to air resistance. This is the case. So it will be downward because air resistance or any form of resistance is like friction. It always opposes essentially the direction of motion. So we can call this one Fk. This is something to consider, but it's not always the case in physics for grade 12s. We normally want to hear the word that says, ignore the effects of air resistance. But if this is not mentioned, do not make the assumption, unless the question itself has an answer leaning towards that fact of ignoring air resistance, and perhaps, other situations being totally ridiculous. Now, consider the statements below for the upward motion. Right. Now, we are told in statement 1 that the rate at which work is done. Now we know that the rate at which work is done, this is a definition of power, capital letter P, by the motor on the box increases. Is that so? But now statement number 2 is also a similar situation. The rate at which work is done by the motor still is constant. Now, we can clearly see that those two statements need us to evaluate them at the same time. Right, now we understand, guys, that power is the rate at which work is done. Right? Right. Now, remember now, this is work done by what? The tension or the applied force. So we know that from physics, we know that work is the force in question. We can say F tension multiplied by the displacement. This time it's in the vertical direction, times the cosine of theta, which is the angle between the direction of motion and the action of the force. Now this is over time. Now from this situation, if we are told that this object is doing constant velocity, it already tells us that this force applied is equal to the balance of the two, or when we add the two together, it balances those two, essentially. Now, we can see that it also suggests one thing, that at any point the tension is the same, meaning this force is constant. Okay, it's not changing. Now, technically, we know that this is constant. Sometimes I use this to show this, but usually this is a sign of a vector. But we can safely say, let's imagine this symbol represents the constant nature of this force. But definitely this one, as this object is moved upward, will increase, isn't it? Cos of theta is nothing but a ratio. So this one is either 1 or -1. But it's never anything else, okay? Okay, maybe in between, but at this stage, we just know that, okay, this one doesn't affect anything. It is essentially a coefficient, which is usually a constant as well. Right, so we know that also the time, as the box is being lifted longer and longer, the time increases. Now we can't tell what's happening here. If we continue refining our issues here, we know that a change in displacement over time spells out velocity. So this is the applied force times the velocity of the object, seeing that this is nothing but a ratio which would become a constant. So it does not affect anything at this stage. Now we can see that, okay, what is this velocity? We were told this force is constant indirectly through the statement itself, but technically the velocity is being given directly this time. Now we can see that this power is equal to the product of two constants. So this means that the power is constant. So this statement is correct, whereas that one is incorrect. As you can see, guys, this is no walk in the park. It's work that needs to be done, and it's technical in nature. So now let's look at the second bunch of statements. It says the mechanical energy of the box increases, and the same statement here, the mechanical energy of the box is constant. Now, is that so? Again, we can evaluate this together. We know that Emech is equal to the sum of the potential energy EP plus kinetic energy EK. But now, we know that the kinetic energy, since it's related to velocity, because this is half mv squared, and we know that the velocity is constant, whereas the mass of the object is constant, and that 0.5 is also a constant. So this one is constant, right? But potential energy is a different story, because potential energy is mgh, and we can see that the height keeps on increasing as the object is being lifted higher and higher As a result, we will see that the potential energy of this object keeps on increasing while the kinetic energy is constant. But now a combination of a constant and an increasing variable will result in an increase in the mechanical energy. So it increases. It does not stay constant. So we can see that the incorrect statements is statement number 1 and number 4. And the correct statements, statement number 2 and 3. Right. Now let's go to the question. It says, which of the statements above is correct? Sometimes the question can say, which of the statements above is incorrect? Right. Now let's have a look. We saw that the correct statement is 2 and 3. So this is option C. Right. Now there can be a lot of questions. I can ask, which of the following statements is incorrect and correct? Meaning, I need two combinations, one being correct and the other one being incorrect. But now the order becomes an important issue. If the word respectively is used, it means the first must be incorrect, the second must be correct. But if that is not stated, it could very well be the reverse. So, folks, from just a single question, we can construct different technical questions for students. So be on the lookout. The reason I'm taking you through these questions, piece by piece and paying attention to detail is to make you understand that, guys, during your training, which is attending classes, practicing examples, solving problems, you definitely need to open your eyes. You cannot be a guy who looks like, you're just trying to gather some knowledge. Remember, the textbook examples after the chapter are just there to cement concepts, but they do not really trick the brain of a student. Yes, they may be of different levels, but usually they don't get to the level of the exam questions, usually. But if you get any exercises, end of the chapter exercises, usually those are at the exam level, of course, of different degrees. So make sure, folks, that you don't leave a chapter without going through those questions. Sometimes you may not have answers. Try your very best to ensure that you can be convinced of how you worked those answers out. Anyway, let's move on. 1.4 says objects P and Q with masses M and 2M respectively. Can you see? It means the first one is of the mass M and the second one is of the mass 2M. Has the same momentum. Okay, so that is very important. So it means the momentum of object P is the same as the momentum of object Q. So this is the equation the examiner is proposing. Small letter p for object P is equal to small letter p, which represents momentum, for object Q. So this is the law. Now whatever we do needs to satisfy that law. Very important. Now, we are told, or rather we are being asked, whether the velocity of P is equal to the velocity of Q. Is that the case? Or is it half the velocity of Q? Or is it twice the velocity of Q? Or is it 4 times the velocity of Q? Now, obviously, folks, since these are of different masses, already this statement is incorrect. But we can test that. But at this stage, you should be a student who can make that difference. Why do I know this? It's because I know momentum is the product of the mass and velocity. So the fact that the masses are different and the momentum is the same, it means the velocities are not the same. So they cannot be equal. But now we have options B, C, and D, which we may not be so sure about. Now we need to work it out. So from the rule that we are given, if we say let the velocity, for example, of object Q be V, then what would be the velocity for object P? So we know that the momentum of P is equal to the momentum of Q. Now, what is momentum is mass times the velocity. At this stage, we can perhaps call it x. Maybe it's better to do that. So this is m times x. So this is going to be mx equals, this time we're going to have 2mv, because we let the velocity of q be v. But now we want to solve for x, so we isolate x. So we can see that x, when we divide by m, the m will take the m. This is 2v. So this means x is equal to 2 times v, meaning it's twice the velocity of q. So the answer is C. So as you can see, folks, these questions are very easy, but they can be made technical, like the case here. One needs to assign variables that were not given and try to make them look the same. That's the skill here. Now 1.5 says a block moves along a rough horizontal surface. So rough means there's going to be, if this is a moving object, so this is Fk, right? This is kinetic friction. While a horizontal force F of magnitude 18 newtons and a constant kinetic frictional force, can you see, we knew that that would be the case, of 6 newtons act on it. Okay, right, so here's the sketch. Now, if the sketch is not given, folks, please ensure to draw the sketch to make sense of the scenario. As you can see, the line which represents the surface this box is on is a smooth line, but there is a mention of kinetic friction. If that was not the case, you never consider kinetic friction, because in physics we've got what we call notations. So a straight line for a surface means a smooth surface, unless there is a mention of friction. So those are the ways of tricking students. Now the question says, which one of the following combinations of acceleration and the total, I hate this word net, for work I prefer the word total, work done on the block is correct. Now we want the correct statement. Now first of all, we can see that 18 newtons is greater than 6 newtons. So we can consider the direction to the right as positive and the direction to the left as negative. Always do this, folks. Choose a direction. Now we can clearly see that in this case, what we call the resultant force, which would be 18 minus 6, this is going to be 12 newtons, is going to be to the right or to the direction of the bigger force. Now, as long as this force and that frictional force acts, this force will also be 12 newtons and it won't change. So in this case, since we are not told much, this means this is constant. Again, we're back to Newton's second law here. Right, acceleration, we know that the force, as long as there's an 18 Newton force applied on the box and a 6 Newton kinetic frictional force, there will always be a resultant of 12 newtons. And in essence, if the force itself, the resultant force, is constant, then the acceleration should be constant, isn't it? From Newton's second law. Again, this is on Newton's second law, but coupling this with work, energy, and power. So remember these things, guys. We can integrate topics. Right, now the total work done on the block, question is, does it increase or is it constant? Now we have to deal with that, because is it constant or is it increasing? But now remember, the total work done, let me write nicely. I don't know why I always write in a hurry. Let me try to be relaxed. The total work done, the total work done is equal to the object's change in kinetic energy. This is the definition, the work energy theorem. Right. But in this case, we have nothing on kinetic energy. But here's something, we've got a surrogate. If we've got a resultant force, it means we're going to have an acceleration. And the acceleration will also be constant because the resultant force is constant. Now this means if we are accelerating, then the change in kinetic energy is increasing because the velocity at different time intervals is going to be different, but on an increasing trend. So this means the work done, therefore, if the kinetic energy is going to increase, therefore it increases. And it is certainly not constant. So which ticks all the boxes is option A. As you can see, guys, these questions are technical in nature. Another student may decide to look at this differently and say the W taught would be equal to the resultant force times the displacement times the cos of theta. Now, we know that the resultant force will be constant since we said as long as the 18 Newton force acts against a frictional force of 6 newtons on a horizontal surface, this is always going to be the case. So this is constant. This is just a ratio, and in fact, the angle is going to be 0 because the resultant force is in the direction of motion. But we know that the displacement, as we continue moving to the right, the displacement increases. And so this means the work itself is going to be increasing. So there's two ways of looking at this, by looking at those two definitions of what we call work done on an object. So that's how we work through these problems. As you can see, guys, these are easy when you are well trained, like my students. But if you're not, this may look like Greek in the exam. Okay, now a star spectrum observed from Earth is red shifted. Now, once you hear this word in physics, folks, you know two things, that this is either a low frequency shift or it's a longer, let's just say a longer wavelength shift. Right. So when we say red, basically we're talking lower frequencies or longer wavelengths, since frequency and wavelength are inversely proportional. So this is very important. Now, again, if we are red shifting, this is already saying we are moving away from Earth. These things are very important, guys, to brainstorm, either in your head or you write them down as you see me do. It helps first when you practice to do this, but as you get better and better, you start to just think about them rather than to need to write them down. Which one of the following statements is correct? Now, we want the correct statement. The speed of light is increasing. No. We consider it as a constant. It is an assumption that we make if we're not told so. Now, this is not true. The star is moving towards Earth. No. The frequency of each spectral line has increased. No. Remember, frequency is low, so it cannot or should not have increased, or could not have increased, perhaps the correct English. Now, the wavelength of each spectral line has increased. The wavelength has increased. That's longer wavelengths. This is true. So this is a true statement. Nice and easy. Usually questions on the Doppler effect involving star movements or the galaxy are usually very easy, although it helps to understand the basics of that, to then make a decision when statements like these are brought to your face. Okay? Right. Because it would make sense on the outset to say, look, if the star is moving away, the fact that it's moving, there's a chance that the speed is increasing. Now, you need to understand that topic-wise, now this is when you become precise with your knowledge, that for the level of study of metric, we assume a speed, in this case, to be a constant, unless otherwise stated. Sometimes we may need to use the concept of relative velocity, which you study in grade 10, when two objects are moving and one is observing the other. So you have to stop one, and whatever you do to the other, you do to the next. A concept in mathematics that what you do on the left, you do on the right. Essentially, logic. Right. Now, we've done that. we move on. Now 3-point charges Q1, Q2 and Q3 are fixed in a straight line. Q1 is R meters from Q2, while Q3 is 2 R meters from Q2, as shown in the diagram. Again, folks, when the sketch is not provided, to win in physics, one needs to imagine the structure and draw the actual sketch. It becomes a lot easier to perceive what could happen and what is unlikely to happen. Now, the magnitude of charge Q2 is small letter q. Good. Right, the next, sorry, I hate this word, you see, the net electrostatic force. Please stop using this word, man. The resultant, man. Hi, man, we're talking science, we're not talking money, man. Come on. Now, the resultant electrostatic force on charge Q1 is 0. Now, what is the significance of this statement? Remember, folks, do not just rush to answering. Ensure you understand what is being introduced for this question in particular, and essentially in principle. Where do we marry the situation right now and the one in principle? So it's very important to realize this. Now, once we are told that the resultant electrostatic force on charge Q1, this is our reference charge, is 0. This is trying to tell us that the force due to Q2 on Q1 is oppositely directed to that of Q3 on Q1, but equal in magnitude. So basically, this means the force, the electrostatic force of Q3 on Q1 is equal to the electrostatic force of Q2 on Q1, but oppositely directed, for them to cancel each other out to 0, because remember, the resultant force is just the summation of the two forces, but because of the opposing directions of action, then they may cancel each other out, or essentially add to each other up. Right, so this is again an examiner trying to give us an equation to work with, and we can safely stick with this one, that technically these must be equal and oppositely directed, because when we put them next to each other and add them together, we should have a negative sign between the two. Okay, so this is very important. Now it says, what is the magnitude of charge Q3 in terms of Q? Now we're going to pull our expression down and say, okay, we want to use this rule because the examiner gave us a formula to work with. But at the same time, in principle, the force here is going to be K. In principle, we're using Coulomb's law. So this is going to be Q1 times Q3, all divided by the distance between the two. So this is going to be 3R all squared, isn't it? Because the distance between Q1 and Q3 is going to be R plus 2R. Then this is going to be equal to K Q1 times essentially Q2, all divided by, what's the distance between them? It's just R squared. Now we simplify and make Q3 the subject of the formula. So we know that we're going to have to cross multiply this and then divide by this, right? So we can tell that Q3 is going to be basically 3R squared is going to be 9R squared times K Q1. We're told Q2 is just small letter q. We're substituting and working our magic. Now we're going to have to divide by K Q1 times the R squared that is already there. Now we can tell that R squared will take R squared, K will take K, Q1 takes Q1, and all is left is that Q3 is going to be 9 times Q. So that is the answer. As you can see, guys, examiners always give you what you need. So the answer is D. In this case, there's no guessing this. It's not even easy to do it by inspection. Without working it out, it's probably going to be very difficult. Again, you can see, guys, time gets chowed. Of course, I'm taking you through step by step, but in the exam, I would answer this thing in less than 20 minutes. Now, you need to work towards that kind of speed, but don't focus on speed. Also focus on the quality of the answers that you can give and ensure that you are sure. And the way to be sure is to work it out as I am taking you through each question. Now 1.8 reads 3 identical light bulbs. Now in physics, this word can be thrown loosely. Now topic for topic, a student needs to know in what regard do we normally say things are identical. Now, essentially, folks, we know that in physics, when it comes to current, electricity, or electric circuits, this is almost always related to resistance. Not anything else, because other issues depend on what current passes through that resistor. If they're in series, they will definitely dissipate the same energy, meaning the voltages across the ends of those resistors are going to be the same. But if they are placed in parallel such that there's more load on one arm versus the other, then they may not experience the same, energy dissipation, or should we say, they may not, if these are light bulbs, they may not really be of the same brightness, I mean, don't go. And then, right, now we're told this is X, Y, and Z are connected in a circuit as shown in the diagram. We are told that initially switch S is closed. Now when switch S is closed, we can see that the current would have to split in this node, because that's the parallel connection. So as you can see, as much as these are of the same resistor, but they don't experience the same current, X, Y, and Z, because they are identical, so they will split the current equally. So they will be of the same brightness, but certainly inferior to that of X, because X gets the total current. Now, a student needs to know that the longer bar represents a positive terminal of a cell, and the shorter one represents the negative end of a cell, and this combination is a cell, right? And essentially we say the conventional current comes off the positive end of the battery. Remember, a combination of more than one cell, we call it a battery here. So we've got a 2-cell battery here, which can be a remote controller at home or something. Now we've got this situation. The conventional current comes off this way, and this experiences the total current, whereas the current splits into two, it splits into two equal components, if you want to call it that. I don't know what to call it. Meaning it's going to be less than the total, but certainly equal for these two resistors. So they will be less brighter than the initial, but they will have equal brightness themselves. Okay, right, now switch S is now opened. So if we open this switch, what are we doing? We are essentially cutting off this branch, meaning we are eliminating the resistor Z. Now it says, how will the brightness of bulbs X and Y be affected? So we are comparing these two now. Okay, so obviously initially this was getting more current, so this should have been brighter than Y. That is definite. But then when the total external resistance increases, because remember the parallel connection decreases the total external resistance, but now when the total external resistance decreases, it does what? It actually increases the current, because these are inversely proportional. Sorry, what does it do? If we increase the total external resistance, we are dropping the current. So if we drop the current, it means X will decrease in terms of power, because we know that, by the way, power in electric circuits generically it's VI by definition. But if we know that, well, they don't experience maybe these ones experience the same voltage, we can use that. But in parallel, they experience different voltages. But now we don't want to end up with a scenario that doesn't work for us. We can refine this and say V, according to Ohm's law, is IR times I. Now P is going to be I times I, is going to be I squared R. Now this is very important to use, because we know that this guy is a constant and the current is the variable here, as well as P. Now we can compare these two, because this is the equation Y is equal to mx, sort of. It's a direct proportionality, because this passes through the origin and we never have a negative current and a negative resistance. So we know that this is going to be a positive slope, which tells us about a direct proportionality. Again, it helps to think about these equations in terms of the functions we learn in maths as models to understand the behavior of these, in operation. Now, bulb X, we said it will decrease because we can clearly see if we decrease the current in this equation, you see, if we drop this, with this one being constant, essentially the power will also drop. So power, basically, the brightness is related to power in electric circuits. All right, so that one is done. Now, bulb Y is a bit tricky in that we need to think more than just guess. Of course, it would be easy to say if we dropped the external current, this one should decrease as well. So a student would be like, yeah, probably this. It would make sense, but that's not quite the case. Be very careful. As much as the current will drop, it will not be less than the split that we had initially. So technically, the current passing through this one will increase essentially. And if we increase this guy for the bulb Y, then we have increased. So literally, this is the correct answer and not the other. So it's easy to make an error here. So the correct option is B here. Now there's more than one way to deal with this, but the easiest way is to assign the EMF. Remember, we're told to ignore the external resistance. So it means the EMF E must be equal to the voltage of the external circuit. So this is good. So we don't have to worry about energy dissipation in the battery. So it helps to just assign values. Let's just guess and say the EMF is 4 volts. And we know that the resistance is independent of the voltage. So we can give this one 2 ohms. 2 ohms and then 2 ohms. Right. Do not make the mistake of using the dependent variable like the current and stuff. Choose 2 independent variables, give values, then work out the dependent. Now we can clearly see that under the first scenario, I'll call it Roman figure 1, we know that the total external resistance here is going to be basically 2 ohms plus the R parallel, which is going to be product over sum, isn't it? So 2 by 2 is 4. Divided by 4, it's 1. So basically this is going to be 1 ohm. Now folks, you need to work it out by yourselves. So this is essentially going to be R external. Maybe let me be more systematic and not be too much of a hooligan. So we know that R external here is going to be, first this one in series is going to be 2 ohms plus the effective parallel resistance. So this one is going to be just 1 ohm. Now, how you work out R parallel, guys, you have to think about it yourselves. Now, these things need you to know how to work fast. So the effective external resistance is 3 ohms. Now, what would be the total current? the total current would be basically the total voltage, which is 4/3. And we can see there that 4/3 is what? Is 1,3 recurring. So this is basically 1,33 to 2 decimal places amperes. Now this would be the total current, and we know that the total current initially would split, hence that one we don't even have to worry about it. But the second scenario, when we cut off the other one, the total external resistance R external would be essentially 2 ohms plus 2 ohms, which is just 4 ohms. Now look at what happens. The total current in this case would be the 4 ohms divided by the total resistance. Can you see this is 1 ampere? Now look at this. Yes, the total current has dropped from 1,33 to just 1. But look at the split in the first case scenario. The split would have to then divide that 1,3 recurring by 2. When we do that, we would get a 0,7 essentially. So rounded off to to 1 decimal place, the split initial would be 0,7 and 0,7 amperes for each one of those two. But look at what happens now. It has increased from this to 1 ampere. Can you see? As I told you that as much as the total current will drop, it will not be less than the initial split when there was a parallel connection. So this can be a numerical way to work out issues here, but of course students, these questions are designed to chow time. You can decide to skip them if you don't know this already, but a student who's discerning stops solving problems by just getting answers. They observe the quality of those answers and look at the different scenarios as to what happens to this answer when this happens, what happens to that. So it takes an exploratory student to essentially know these things so that in the exams you don't have to waste a lot of time figuring things out. But it's safe to skip such questions, to come back to them later when you know you've banked a lot of marks on other questions, so that you don't sit here and lose time when you haven't answered easy questions that you may still score good marks on, only to find that even your answer here still becomes wrong even after wasting that time. So for safety purposes, these are good questions to skip, to come back later. Even if you guess, it's not a problem. But remember, the 2 marks that you would get from this question can be a difference between getting that distinction and not getting it. And you know the implications, right? It can be a difference between a pass mark and a fail. So you know the implications thereof. So as I'm saying, take the safety measure, but remember, this may impact on your final mark if you don't do it right. So make a habit of making sure you work efficiently, but essentially thoroughly. Right, so guys, we took an hour to do MCQs, but anyway, this is just to train a student, especially those who want to upgrade, because you will feel like this is torture, but now you get to see this is not. 1.9 says, how does the commutator in a DC motor ensure that the coil rotates continuously in one direction? It's only because the current is kept in one direction. Because remember, we know that a current carrying conductor has a magnetic field around it, right? So if the current keeps the same direction, the magnetic field will also be in the same direction. And that means this will experience a force in the same direction. And that would mean the coil would spin in one direction. Okay, so right, now this is it does this work by reducing friction. It has nothing to do with this. By converting AC to DC, not at all. By reversing the direction of the current in the coil, this is true, okay, because of the split ring commutator. The commutator here is what we call the split ring commutator. So that one is the one, okay. Now this is by maintaining electrical contact between the external node. These are the carbon brushes, so it has nothing to do with the commutator. So essentially, guys, this is C. Again, if you don't understand, I mean, usually questions on the electrodynamics are easy, but you can tell this one will challenge you if you don't understand how a current carrying conductor behaves when it is placed in a magnetic field and why. Right. 1.10, the last question, says light of different wavelengths is incident on a metal surface. Okay. Now this is the photoelectric effect. Now which one of the following graphs shows the correct relationship between the maximum kinetic energy of the photoelectrons, EK max, and the inverse of the wavelength of the incident light? So what is this, guys, in general? Now it helps to understand the inverse of the wavelength is essentially frequency as a surrogate. So a student who knows this, we know that as the frequency increases, or the inverse of the wavelength increases, the kinetic energy will also increase, of course, from threshold until God decides it's over. So automatically graph C here for a student who knows what's cooking, because we know that as the frequency increases from threshold to whatever value, the kinetic energy is going to increase, because threshold is this frequency right here. So it's not this graph, it's not this graph. We never deflect negatively in this case. And essentially this is nonsense as well. So option C is the correct one, by understanding that this is a surrogate for frequency. But if you don't know this, you would be dead. But here's how to make sure that even if you didn't know this, you can still work your magic. Remember, we know that the energy of a photon, which is going to be the Planck's constant, times the frequency of the whatever we call this, is going to be equal to the work function of the matter plus the kinetic energy maximum of the photoelectrons. So this is the photoelectric equation. In fact, the work function is going to be the Planck's constant times the threshold frequency. Right. Now, let's think about this now. What happens here? We are talking about now the inverse of the wavelength. So how did we get that? We got it from another equation which says C is equal to frequency times lambda. Now, if we isolate frequency, we know that frequency is going to be C with the speed of light in a vacuum divided by the wavelength. And if we refine this equation further, we can actually take C as a common factor and remain with our lambda like that. So this is a constant, this is a variable. Can you see that? So essentially this could be a surrogate for frequency, but we know it's not the exact measure, but it can tell us the proportionalities. And as you can see, guys, if this is a constant, if this increases, right, technically the entire thing drops, right? But when the entire thing increases, what happens to the frequency? It also increases. So this is very important to know how to work with these brackets, guys. Now if we take what we have here and go plug it in our equation, we know that we've got the Planck's constant into, instead of frequency, we're going to write C over lambda, right, is equal to H times the threshold frequency plus EK max. Now this is what we have, but what are we going to see? On the y-axis, we've got EK max for each of these graphs. So it means we make this one the subject. So if we do so, we know that EK max is going to be equal to this issue here, HC, if we take them as a common factor, and then we get our lambda doing the things there, inverse of it is going to be subtracting the work function. Right. Now, let's have a look here. This is an equation that matches the model y equals mx plus c. Right, my pigeon is moving around here, so I don't know why it doesn't sleep. It likes to sit on my curtain. Now, folks, which one is the constant? This guy. So we can see that the gradient, since this is always positive in principle, these are constants we get from the page, the information sheet. So these are constants. So if they are constant, it means the gradient should be positive. So that already means this is wrong, this is wrong, this is a potential, this is a potential. Okay? Right. Now, we think again and say, okay, all right, okay, we understand something. We look at the y-intercept. What is the y-intercept? It's the work function. So it's usually negative. It's never zero or something else. Okay, maybe let me not say never zero, but we understand that this is on the negative. So usually this should be negative. So where do we see the negative sign? There. If it comes in front of this, this should be our work function. So where is it here? This is 0. It's not negative, so it's wrong. If we draw this to the y-intercept, this is positive, essentially wrong. If we extend this, it's negative, which is correct. Can you see that? So we know that, okay, the y-intercept is correct in this case. This one is 0, it's wrong. So can you see now, we understand two things. The gradient must be positive and the y-intercept must be negative. But for a straight line equation, you understand one thing, that the x-intercept would represent the threshold frequency. Now, what happens to a positive gradient and a negative y-intercept? So it is never possible to have a graph like this, where we've got a negative y-intercept and a positive gradient that has a negative x-intercept. So this is only possible if the graph is like that, or we get a positive y-intercept and a negative x-intercept. Otherwise, we can never have a positive gradient with a negative y-intercept and a negative x-intercept. So this is positive, so which is correct. So there are many ways to analyze this. As I said, if you understand this photoelectric equation, and my students, by the way, we dealt with MCQs on the photoelectric effect, and we looked at graphical representations of this nature. And I expect them to have scored those 2 marks in this question. Otherwise, guys, this is how we work through these problems. And if we understand functions, as I said, we know the equations that govern the issues here, like this equation over here, and analyzing it with the understanding of functions in mathematics, you would know how to pick the right answer, even if you've never seen these graphs before. But for those who have and understand how this works, they would easily pick out the correct answer without suffering and wasting time. Either way, I have shown you how to still win, even if you weren't so sure. How to be sure by using the knowledge of what you have done. Okay, guys, this is it for this question. I'll see you in the next question. Goodbye for now.